Hello viewers, in my last lecture I have introduced you the index numbers and then we have discussed how a index number can be constructed. We know now that an index number is a measure of average change in the prices of a group of commodities over a period of time. We can also construct, like the price index numbers, the quantity index numbers as well as the value index numbers, and there we consider the quantities or the values of different items in place of the prices. Also, when we construct the index numbers, we have taken the geometric mean or the arithmetic mean of the price ratios of different items. And while taking the geometric mean or the arithmetic mean, or the third method which we discuss is the aggregative method, we have seen that either we have given them the equal weights, that is the different items were given the equal weights or the no weights at all while combining them. But as we know that in most of the cases, like in a family's budget, we know that the 50% of the income, for example, is spent on the food items, 10% say on education and say only 1% on the entertainment. Now, if we give equal weights to all the items while combining them in order to have a formula for the index number, then it is not proper. Therefore, it is better or it is more appropriate to give different weights to different items depending on their utility or their importance in the family budget. So, in today's lecture of business statistics, we shall continue with our discussion on index numbers. In particular, today we shall see how weighted index numbers due to Laspeyres, Paasche, Fisher and others can be constructed. Now, let us see how we select the weights, that is what should be the choice of weights. The accepted practice is to use value or expenditure figures of an item as weights, that is the W is equals to the P times Q, that is price is multiplied by the Q, and when we take the prices and quantity of the base year, then this weight is equals to P naught times Q naught in particular. So, for the ith item it will be P naught I times Q naught I, that is this gives the value or amount of expenditure in the base year, or we can take W as the product of P1 Q1, that is value or amount of expenditure in current year. Also, the value of W can be taken as P naught times Q1, or in particular for the ith item it will be P naught I times Q1 I. It is hypothetical value of the ith commodity in current year at the price of base year. The weighted index numbers are given by various authors. They are the Laspeyres, Paasche, Dorbish and Bowley, Walsh or Irwin Fisher and Marshall and Edgeworth. Now, first we shall discuss Laspeyres and Paasche's index numbers and see how these index numbers are constructed. Now, first we shall discuss in general how a weighted index number can be constructed. So, you look at this formula I01 as we denote the index number by I01. Now, this is equals to sigma P1I divided by P naught I multiplied by 100 times the Wi, that is the ratio P1i divided by P0i is multiplied by Wi and divided by sigma Wi. That is, we can see that I01 is nothing but the weighted average of these price ratios. Now, when we want to construct the less pairs index number, then the value of Wi is equals to P0i times Q0i, and this gives me the less pairs formula, which we denote by capital L01, and this is on simplification I get it as sigma P1i times Q0i divided by sigma P0i times Q0i, and of course we multiply it by 100 in order to have the value of the index number in percentage form. Now, in case of the Paasche index number, we take the value of Wi is equals to P0i times Q1i, and the formula given by Paasche we denote here by P01, and this is on simplification gives the sigma P1i times Q1i divided by sigma P0i times Q1i multiplied by 100. These index numbers can also be obtained directly from the weighted aggregative index number. The weighted aggregative index number is denoted by say I01 is equals to sigma P1i times Wi and divided by sigma P0i times Wi. As we know that P1i is the price of the ith commodity in the current year, whereas P0i is the price of ith commodity in the base year. So, here for the less pairs method, if I take Wi is equal to Q0i, then it gives me the less pairs formula of index number, and when I take the value of Wi as Q1i, we see that it gives me Paasche's index number. Now, let us see how these index numbers are being computed, and look at this example. In this table, in the first column, the items or the variables name are given like bread, potato, chicken, and the prices of these items are given in the year 1991 and of 1995. The prices in the base year and the current year are given in dollars and in the units which is mentioned in the brackets here. Now, here the weight is taken as the average quantity consumed in 1991 by a family. That is my Q0i's. That is, for the bread, this weight is 200 loaves, as so many loaves are consumed by a family in a year. And like potatoes, the value of Q0 is 300, and for the third item it is 100. And then we find out the product of P0i, Q0i's for each item, and this is how we complete this column, and the total gives me summation P0i times Q0i, and the next column similarly is of the product P1i times Q0i, and the sum of this is sigma P1i times Q0i. So, the substituting the values of sigma P1i Q0i and sigma P0i Q0i as 985 and 811 gives me the value of the less pairs price index number. Now, let us see how Paasche's index number can be computed. In this table, we see that the first column gives the name of the items under consideration. The second column gives the volume of sales in the year 1995, where the year 1995 is a current year and the base year is 1990, and here the prices of the items in the base year and in the current year are given in these two columns. Then the next column is of the product of P0i times Q1i, and the last column is of the product of P1i and Q1i's. and here we have the items like milk, eggs, cheese, sandwich, gasoline, calculators. Now here we see the change. While constructing the Laspeyres index number, we have considered the quantities of the base year, whereas in this construction we take the quantities of the current year, that is of the year 1995, and then by using the Paasche formula, which we know is sigma P1i times Q1i, and the value of this factor is 273.70, and divided by the factor sigma P0i Q1i, which is 211.66. So, this will give me the value of Paasche index number. Now, let us discuss the other index numbers. Here, the first one is the Dorbish and Bowley's index number, and it is nothing but the average of the Laspeyres and Paasche index number. That is, I01 is equals to half times L plus P, that is L01 plus P01, and we get this formula for this index number. The other index number formula was given by Marshall and Edgeworth. In this formula, the weights are taken as the average of the quantities in the base and of the current year. That is, the Wi here is equals to Q1i plus Q0i divided by 2. That is, if I consider the weighted aggregative index number, that is summation P1i times Wi divided by summation P0i times Wi, the value of Wi is the Q1i plus Q0i divided by 2, and this formula on simplification gives me I01 is equals to sigma P1i times Q1i plus Q0i divided by sigma P0i times Q1i plus Q0i. And index number due to Walsh, who gave it in 1901, and again by the Fisher in 1920. This formula is nothing but the geometric mean of the Laspeyres and Paasche index number. That is, I01 is equals to the square root of the product of L and P. Here L denotes the Laspeyres index number and P denotes the Paasche index number. That is, the full form of this index number is given here. This formula has been much accepted due to its desirable properties, which we are just going to discuss. Now, we have a number of index numbers by different authors. Now, the question arises that which index number is more appropriate to use, and for that certain criteria has been given in the literature, and two of the most important criteria are the time reversal test and factor reversal test. Now, first we shall discuss what do we mean by a time reversal test. Now, the time reversal test is given by this formula I01 times I10 must be equal to 1. That is, if any index number satisfies this equation, then we say that this index number is appropriate according to this criteria. Now, what is here I10? We know that I01 is the index number where 1 denotes the current year and 0 denotes to the particular base year. If my current year is the 2000 and the base year is 90, then the 1 denotes the year 2000 and the 0 denotes the year 1990. So, when I take I10, it means now I have interchanged the base and the current year. That is, now 1990 is taken as the current year and the base year is taken as the 2000. So, the product of that must be equal to 1. That is what the time reversal test says. Say, for example, here we can see that I01 in this figure the base year for this is 1990 and current year is 2000, where in case of I10 the base year and current years are interchanged. So, if suppose I am using the simple aggregative index number, then we know that I01 is equals to sigma P1i divided by sigma P0i, and using the same formula the I10 will be sigma P0i divided by sigma P1i. So, that is the only difference, and we see that if we multiply this index number, that is I01 with the I10, we see that it gives the 1, that is the simple aggregative index number satisfy this criteria. Or if an index number does not satisfy this criteria, then it gives me the error, that is E1 equals to I01 times I10 minus 1. So, this equation gives me the measure of error in that particular index number. Now, we have seen that the simple aggregative index number satisfies the time reversal test, but let us see which are the other index numbers satisfy this criteria, and such index numbers are the simple index number based on geometric mean, simple aggregative index number as we have just seen, and Marshall and Edingworth's index number, and Walsh or Fisher's ideal index number satisfy the time reversal test. Here we note that Laspeyres, Parsons and Dorbish and Bowlage index numbers do not satisfy this criteria. Now, we shall discuss the other criteria, that is the factor reversal test. This criteria is given by this equation, that I01P times I01Q is equals to V01. Here this I01P denotes the price index number using by any one of the formula which we have discussed, and I01Q denotes the quantity index using the same formula. That is, if we are using the Fisher's ideal index number, then for price also we use the same index number, and also for the quantity index. Only thing is that in place of the prices we shall replace the quantities, but we shall use the same formula given by the same author while calculating the I01P and I01Q. So, the product of this must be equal to V01, where this V01 is equals to sigma P1i times Q1i divided by sigma P0i times Q0i, and this is known as the value index. For example, if we are considering the Laspeyres index number, then the Laspeyres price index number formula is given by this, as we have discussed earlier, and the Laspeyres quantity index number, which is denoted by L01Q, will be equals to sigma Q1i times P0i divided by sigma Q0i times P0i. Here we can see that in these two formulas, the P's are replaced by the Q's, and the weights has taken here as the prices of the commodities in the base year. So, L01P and L01Q, these are the price index numbers and quantity index numbers using the Laspeyres method. So, if the product of these two index number is equal to the value index, so we say that the Laspeyres formula satisfy the factor reversal test, but unfortunately we can check that this Laspeyres formula does not satisfy the factor reversal test. Not only the Laspeyres, but the other formulae which we have just discussed like Parsons, Marshall and Edingworth, they also do not satisfy the factor reversal test. Now, here we observe that the Fisher's ideal index number satisfies the factor reversal test. We know that the Fisher's index number or in particular the Fisher's price index number is given by this formula, whereas the Fisher's quantity index number is given by this formula, that is I01Q is the geometric mean of less pairs and pass-change quantity index numbers, and this is given by this formula. So, if we multiplied this I01P and I01Q, then this will give me the value index. So, this is the only index number which satisfy both the criteria, that is the time reversal test as well as the factor reversal test, and therefore we say that the Fisher's index number or the Walsh index number is an ideal index number. So, again it may be noted that none of the other index number satisfies factor reversal test, that is both the tests are satisfied by the Fisher's index number. The Fisher's index number originally was given by Walsh in 1991 as the geometric mean of index numbers due to less pair and pass-change. That is, we have seen that this I01 is equals to the square root of L times P. Erwin Fisher in 1920 called it an ideal formula as it satisfies both the time reversal and factor reversal test, as we have just seen. Therefore, it is known as Fisher's ideal index number. There is one more criteria which an index number should satisfy, and that is the unit test. This criteria says that the index number must be free of the units. For example, the simple aggregative index number does not satisfy this criteria, whereas the Fisher's index number satisfies this criteria also. There is one more criteria which we are going to discuss in my upcoming lecture, and that is known as the circular test. So, in all there are 4 criteria. We prefer that an index number should satisfy all the 4 criteria, but it is difficult to have an index number which satisfies all the 4 criteria. Even the Fisher's index number, we shall see, does not satisfy the circular test, but it satisfies all the first 3 criteria, that is the unit test, time reversal test and factor reversal test. In today's lecture, we have seen how weighted index numbers can be constructed, and then we have discussed the criteria for an index number to be satisfied. Here we have discussed in particular the less pairs, pass-change, Marshall and Edgeworth and Fisher's ideal index numbers, and in particular we have discussed the time reversal test and the factor reversal test, and then we have seen that the Fisher's index number is the only one which satisfies the time reversal test and the factor reversal test, and therefore this index number is called or known as the Fisher's ideal index number, and this index number we know that originally given by Walsh in the year 1901. Thank you.